It's great to see so many people here. We're very excited to have Gregory Abowd here from Georgia Tech. Gregory, as I've told him, is our inaugural speaker in our new computer science series, Distinguished Speaker Series. So, no pressure.
None felt.
No pressure. We really wanted to actually jointly co-host this with Bayard Jones Seminar and also Lisa Marsh's Center for Technology and Behavioral Health from the Weiser Medical School. Why? Because Gregory's research is highly cross-disciplinary. In fact, if you take a look at the types of things that he's done in his career, he's done everything from sort of pure ethnographic styles of research to building novel hardware, circuits, sort of EE types of things. And today, I almost think he's morphing into a material scientist based on the title of his talk, which I'm not sure what it's about, so that's exciting. Gregory is the Regents Professor of the School of Interactive Computing at Georgia Tech, where he's pretty much spent most of his academic career. Prior to that, he did his PhD in Oxford in England, and spent three years in York doing a postdoc. That's surprising from his accent. He didn't know the Yorkshire accent at all. I just thought I'd tell you a little bit of sort of inside information about Gregory, because he's sort of fun-loving guy. If you chat to him for a few moments, you get that sense, and his excitement for research and talking to people. But he has actually graduated 30 PhD students in his career, and has a family tree of 100 PhD students. That's like an army of people across the country. And many of these PhDs or doctors are full professors in really top universities in the States, and they themselves are actually, creating new areas of research. So that's pretty exciting. And it was some of these students that gave me some inside information on him. They love to apparently play practical jokes on Jeffrey. Gregory. I keep calling Jeffrey, but in fact, English people do that. Gregory. For example, when he got tenure at Georgia Tech, they filled his room with balloons. Built. Not just a build. Not just a few balloons. When he got promoted to full professor, they went a step further and they covered everything in his office with aluminum, or I should say aluminium foil.
Everything.
Every book.
Pencils, books, sheets of paper, ceiling tiles.
But the piece de resistance was they put a porta potty door on the outside of his regular door. And there is a side story to that, but I'll not go into that.
If you want to know the side story, not while we're recording.
Yeah. There's a side story. But it's clean. But there's a side story. What really tells you a lot about Gregory, and I think if I was to ask him what does he value most in his career, is it the awards that he's won, his ACM Fellow, etc., or all the grants or NSF centres that he's run? I would imagine he would say no. It's the pleasure I gain mostly is through the students I've worked with over the years. And really his students do adore him. He adores the students. But I'll finish up by saying, after 10 years of the porta potty door being on his door, he was getting letters and email from people at Georgia Tech asking him to take it down because it was fire risk. That door stayed there for 10 years, I believe. Anyway, interesting factoids. So I'd like to take this moment to welcome Gregory and ask us to give him a good Dartmouth welcome.
So if you get bored during the talk, and you have a connected device, which probably few of you have, you can look up. There was a story that was released by Georgia Tech last month that talks about the toilet and my academic family, so you can read about that. What I'm going to talk about today is an attempt to try to inspire a generation or two of research into the future. And I'll refer to this as the fifth generation of computing, and I'll explain why I count it as the fifth generation. And one way to think about this is I'm going to revisit the vision of the third generation of computing, which is Mark Weiser's vision of ubiquitous computing. And I'm going to reveal what I think are some limitations to being creative in Weiser's vision of ubiquitous computing, given the context of when that vision came about in the late 80s, early 90s. And I'll try to suggest a new context, technological context of 2018 that might allow us to think differently about how we might achieve this notion of ubiquity. And that will be motivated by a technological innovation that I'm referring to as self-sustainable computational materials. And I'll describe what those are. And I'm going to give only one example. I have a second example, but my guess is that there are people in this audience who might be in the reviewer pool for a paper that was recently submitted, so it would not be appropriate for me to show that. If you're not one of those reviewers for the Chi conference, you can come to me after the lecture and I'll show you a really cool demo of an additional example of a computational material. And then I'll close by describing 5 different research opportunities that I think happen because of this notion of computational materials. So first, let's give you a quick summary of why I am going to talk about the 5th generation of computing. And that's because a way I think about how to structure the history of interactive technology in computing is thinking in terms of these generations. And these generations are defined in terms of a time frame in which one or a small number of people presented a vision. That vision was usually driven by the observation of a new kind of technology or technologies that were emerging at that time. And those technologies tended to have an interesting relationship between how many people interacted with how many instances of this technology. But what drives all of the adoption of these technologies in time are the applications. And I think of applications in terms of the initial set of applications that drive adoption, and then the follow-on applications that take advantage of the fact that people have invested in that canonical technology, and you can do things with that. So just to quickly then go through 60, 70, 80 years of computing history in 20 seconds, we have the first generation of computing, which was the mainframe, many people interacting with one device. Things in the war really were the initial reason why people adopted these technologies, and after the war, data processing applications drove, leveraged that investment. It was typically at the organizational, large company level. Then you have the personal computing generation in around the late 60s when those visions first came about. The idea there was that each person could have his or her own device. Some of the initial driving application was the spreadsheet, and an example of using a metaphor from the physical world in the electronic world to make it easier for people to understand how to operate that computing program upon first exposure. And then there were a number of other follow-on applications that happened. Initially, the adoption of the personal computer was again in corporate environments, but then it started to spread outside of business environments. The first really important generation that I want to talk about is the one that was defined the ubiquitous computing revolution. And Mark Weiser wrote this article, The Computer for the 21st Century, and the title of this talk is a direct play on that particular title, because this is going to be the influence of what I'm going to talk about later. Weiser foresaw not one new canonical technology, but 3 classes of technology that were distinguished by how large they were, and that size dictated the ownership and relationship that individuals had with the particular technology. I'm not going to go into a lot of detail. I will tell you this: if you're in computer science and you haven't read that essay, you need to read that essay. It's one of the most influential essays from the 90s that drove a lot of computer science research. People-to-device ratio is now that each person would have many of these devices or would interact with many of them throughout their lives. And if we think about the smallest scale, the inch scale, the applications that drove initial adoption were calendar and contact management, personal digital assistants, and human-to-human communication, talking on mobile phones, which eventually merged together. And once you had that initial adoption, lots of other kinds of capabilities took advantage of the fact that lots of people had these connected devices with them most of the time. A couple years ago, I thought that, well, it actually been a long time since Weiser had given this vision of ubiquitous computing, and certainly technology has moved forward. So I wrote an essay that I'm not going to talk much about, today that talked about what were the technologies that emerged about 15 to 20 years since Weiser's vision that he did not really foresee. Technologies of cloud computing, technologies of programmatically introducing humans back into computation, so using crowdsourcing and human computation. Something that I refer to as the shroud. You can see the pattern here, but the shroud was talking about devices on your body and Internet of Things devices, so a covering over the physical world that connected the physical to the digital world. And then something that was not actually written in this article, but rhymes, and is appropriate, are technologies of continuous speech recognition, so allowed technologies. And believe it or not, I talked about this work for about 9 months before someone pointed out to me that these all rhyme with my last name. And I did not know that. That was not the intention. But yes, if you don't believe, you should believe that because it's the cloud, crowd, shroud, allowed, so says Abowd. Okay. And there, one interesting thing was an observation of what was the driving application that merged all of these technologies together. And I give an example of personal navigation and tour guides as how we take all of those technologies today and give people the ability to be their own personal tour guide without any preparation. And the general version of that, which I think is something that is an active focus for our opportunity for research today, is what I refer to examples of on-demand harnessing of expertise, or be your own X. Whether that's be your own health counselor, be your own teacher, be your own tour guide. These are opportunities to leverage all of these kinds of technologies to provide those kind of capabilities. And it is related to a project that I've informally at least worked with Andrew on in terms of how you might allow individuals on a campus to become informed and become their own mental wellness coaches because they have access to information about their activities, and you can leverage cloud and crowd technologies to provide them advice in the moment. That's kind of the vision that I saw for that kind of work. But that's all groundwork for, these are all kind of, that's the history of computing, believe it or not. But what this sets up is for me to talk about something that's about the future. And I was talking to people this morning trying to contrast what I did when I was a graduate student and a postdoc to what I tried to do when I became a faculty member at Georgia Tech. I was trained as a mathematician, and I was very good at providing elegant formalisms that described phenomenon perfectly, but they were all things that we already knew about. So I wasn't providing any insight into where computing might go. I was, in some sense, I was the guy that walks behind the parade and cleans up the horse poop or whatever. I was just making things that we already knew that had passed, tidying them up and giving them a formalism. And I said I wanted to do something that kind of influenced the future of computing. And so I'm going to try, and I've been trying for the last 2 years, to think about a way of providing a vision for what might come next in computing. And that's the attempt here. So it's moving beyond Weiser's vision of ubiquitous computing, but you'll see that it's actually maybe coming back to that vision and seeing how we might approach that. So by the end of this talk, I will at least have filled out these 2 cells, and I will hint about what might be the motivating applications. So here is the first line of that famous essay: the most profound technologies are those that disappear. Who knows the next line? Right. They weave themselves into the fabric of everyday life until they're indistinguishable from it. So Weiser meant this metaphorically. He started this work in 1988. This article was published in 1991. But today, we can start to interpret that much more literally, because of the kinds of technologies we have available to us. So I am influenced by our current technological state to reinterpret that. And it's often a good research practice to go back to work in the past and look at what motivated that work and think about how that motivation might be reinterpreted in the context of today. It's a very renewable kind of research agenda. You don't have to come up with ideas. You just go look at other people's ideas and you reinterpret them in today. So it's a nice strategy for keeping you going. But what was the kind of influence that Weiser had? And Weiser's influence came from Moore's Law, because we were in the heyday of Moore's Law in the late 80s and early 90s. And what is Moore's Law? Well, this is literally what was written as Moore's Law in 1965 and revisited in 1975. That the number of transistors you can buy for some amount of money, $1, it will double every 1 to 2 years, 18 months, and it's because of increasingly ingenious ways of integrating the manufacture of these integrated circuits. So that's really what Moore's Law is. It's an economic statement, and it was an empirical observation done in 65 and verified again in 1975, and has essentially driven the semiconductor industry up until about 2-3 years ago. This is how we kind of colloquially understand Moore's Law. We see statements like this. So this is from 3 or 4 years ago, saying that a single Apple iPhone 5, so that's, it's 6 or so generations back, and so that's maybe 2012 or so, has 2.7 times the processing power than the 1985 Cray 2 supercomputer. What's so relevant about the Cray 2, the 1985 Cray 2 supercomputer? Well, it was the most powerful computer on the planet in 1985. And 85, 95, 2005, less than 3 decades later, you could own for a fraction of the cost more than that and hold it in your pocket. Right? And my guess is that most of you are not surprised by statements like that because we see statements like that all the time. Right? We come to believe that this is always going to happen. And the point I want to make to you is that when you operate in that context, it influences the way you think creatively about how you might use computing and what its possibilities might be in the future. So this produces what I will call Moore's Law thinking. And it's influenced by this statement. Computers are always going to get smaller and more powerful. And if you have that ingrained in your psyche, then here's the kind of thing that happens in a research setting. You have you have lots of different examples of where this might happen, right? So in portable computing, we see an example. This is the computer I took as a grad student in 1986 to Oxford. And I was the bee's knees. I was everything, right? I was carrying around this luggable, looks like a sewing machine when it's wrapped up. And for less than the $2,500 I paid, this is what in 2016, 2017, the Microsoft Surface 4 looked like, which is infinitely more powerful, infinitely way less, and does many more things. Okay, we're used to that. We see that with telephony, mobile phones. This is the mobile phone that you probably saw at the beginning of the sequel, Wall Street, when Michael Douglas is checking out of prison and he's getting his mobile phone back, this big brick he gets, and we see today this kind of device where you can add and subtract different kinds of capabilities onto your mobile phone. It's cheaper, it's much smaller, it's much more functional. We look at augmented reality, what it looked like in 1999, what it looks like today. We see virtual reality in 1999, and what you don't see here is the Cray supercomputer that's attached to that little umbilical cord. And here's what we see for today, these sexy glasses that you can wear that will give you a virtual reality experience. And we are just so used to this, right? What does this mean in a research context? Well, a student comes to his advisor or her advisor and says, here's my prototype system, doesn't run in real time, kind of bulky, but the idea for the future is there. And what does the advisor say? That's okay. Moore's Law will take care of those problems. Go ahead, publish it, right? Because those other things are, how many people do we have that are engineers here? The following sentence I say with the utmost respect. But in computer science, we'll say the fact that it's a bit bulky and doesn't run in real time, that's just an engineering problem. Right? And we say that with respect because engineers make things really work. Computer scientists, we just suggest and then we throw it over. Right? But this is the mindset when you have Moore's Law thinking. Well, there's some problems with that because depending who you talk to, Moore's Law is over. But if you talk to me, whether or not Moore's Law is over, the threat that we think Moore's Law is over has me kind of going, Moore's Law thinking may finally be over. So we may have an opportunity to think creatively about how we use computing devices if we're not only thinking about progress in computing being because we can shrink things down, make them smaller and cheaper and faster, and that's the only measure of success that we think about. So how do we think differently? Well, there's some things that I want to preserve. And I think what Weiser was talking about in his vision of ubiquitous computing is that advances of computing are coming about because we're providing compelling applications that take advantage of the fact that computing capabilities are more and more around us and available to us. And I think that's still an aspiration that we can shoot for. We are nowhere near the vision of ubiquity that Weiser talked about in his 1991 essay. And I would say that the inch, foot, yard scale and the Moore's law thinking is not going to get us there. So to continue, we have to think differently about what it's going to mean for us to get more ubiquitously available and compelling uses of computing applications by doing things other than just shrinking things down and increasing the density of devices or transistors in a particular volume or area. So the idea that I want to propose is to rethink how we make computational devices so that they can become truly more ubiquitous. So I'll introduce what I think is a potential canonical technology for the 5th generation, and it's inspired by at least 2 different trends that have been happening over the last few years. Some at Georgia Tech and at other places. But I'm going to show you examples from my colleagues at Georgia Tech. So my colleagues in electrical engineering have been working for about 5 years or so on ways to print computational capabilities or electronics on paper or flexible, thin plastic substrates using traditional commodity inkjet printing capabilities. So printed electronics is pretty widespread now. Something that you may not be as familiar with, in the nanotechnology world, there have been people who have been able to grow computational devices. So at Georgia Tech, they have demonstrated a way to essentially grow an NPN transistor, and many of them simultaneously using chemical deposition. There's a little gold dot here that essentially allows you to grow a column of material, and depending on the chemicals that you have in the vapor around there, what will grow will have particular properties, and if you control the flow of those vapors, you can control what the material is. So you can basically produce an NPN junction and produce something that works like a transistor. But you're producing these very differently than traditional photolithographic techniques for integrated circuit design. So this was possible over the last 4 or 5 years. And I was very fortunate that a number of my colleagues in chemical engineering and material science came to me saying, we can do these kind of things. We think we can produce 2-dimensional materials that have an arbitrary number of devices hooked up in arbitrary circuitry and 1-dimensional cables that can be woven into threads. But why would we care? And I said, why would we care? Didn't you read Mark Weiser's article? And they said, Mark who? So they went and read that, and they said, oh, yeah. I said, you don't even have to read the whole article. Just read the first 2 sentences, and we'll have a test tomorrow. Okay? And they read that, and they said, we see why you might be interested in this. And this had me thinking that what we might be able to produce now is manufacture computational materials. But what is a computational material? Well, it's a material that is self-sustaining. That means it harvests or otherwise gets delivered to it the power needed to do things that computational devices do. What does a computational device do? Well, it stores information, it computes logical operations, it senses things from the physical world, it actuates, provides some kind of output, and it communicates within the material and between materials. Okay, so that's a self-sustainable computational material. But to really have impact, and this is where the manufacturing side comes in, you need to be able to manufacture it in very large quantities, very cheaply, and for it to even happen, people have to think that they want this in their lives, so it has to do interesting things. So we now have a kind of report card for what it means to have a computational material. You need to satisfy these criteria. So I'm going to give you an example over the last year from my lab. This is some work that will be presented at the UbiConf conference in 2 weeks in Singapore. And it's an example of using a harvesting technique that is pretty ubiquitous in our everyday world, but not very much exploited by computer scientists. It's called the Triboelectric Effect. And a really simple way to understand it is if you've ever, as a child or as an adult, taken a balloon and rubbed it on your hair and generated a static field of it, you can essentially place that balloon on the wall and it will stick. There's a transfer of electrons between two materials when they either come in contact and separate or slide across each other. And this happens pretty much between any two materials. It just so happens that certain materials, when paired together, exhibit this effect in a more pronounced way. So if you're smart about which materials you produce, then you might be able to generate certain electrical power in interesting situations. So we exploited this in the following way. So here's a quick video that's going to show you this Saturn project.
What if objects and surfaces around us could hear? We present Saturn, a flexible thin material that can easily be embedded on everyday objects to enable them with self-powered sound sensing and sound energy harvesting capabilities. Saturn consists of materials which are thin, flexible, and cheap. Paper and a dielectric called PTFE. The paper has a series of holes laser cut in a specific pattern. Both layers, PTFE and paper, are coated with a thin conductive layer of copper and joined together using glue dots in a grid-like pattern. When sound reaches Saturn embedded into an object or surface, its structure microvibrates, resulting in both layers getting in contact, generating negative charges on PTFE and positive charges on the copper-coated paper. As the layers separate, potential differences built over the two copper layers, causing a current to flow towards PTFE. The next vibration results in the layers getting closer and in contact again, resulting in a reverse direction of current flow that completes the cycle of electricity generation. The structure, material design, and method of embedding Saturn on objects has been optimized to maximize the recovery of sound and the power harvested from this electrical signal.
So I'm going to pause the video at that point. So this is essentially thin, flexible, cheap materials, relatively easy to manufacture, that is a self-sustaining sensor, meaning that the phenomenon that it is sensing is the phenomenon it uses to harvest the power to do that sensing. So it's going to be able to record or capture the sound that is incident upon the surface, and that sound is what's causing the vibration that uses the triboelectric nanogeneration effect to create the power to acquire the signal. So if we look at the report card for a computational material, this is something that harvests the power to essentially do its own sensing, and it's relatively cheap to produce. It's not something that's computing, it's not something that's storing, it's not actuating, it's not communicating, and I haven't shown you anything interesting that it's doing. Be patient. But if we are smart and look at our field and say, well, what things could we improve here to make this do something interesting? And I will say there are two places we could look. We could have it do some local computation, and then some actuation so it could actually respond to something. Or we could allow it to communicate off the device to the rest of the computational world and have that do something with it. Turns out that's an easier path to follow, and this is something that we'll demo at both UbiComp and at WIST in a couple weeks. There is this phenomenon called analog backscatter. Radio frequency signal comes to an antenna, the antenna reflects it back. That's the backscatter. Well, you connect that antenna to a little junction field effect transistor, a JFET, to essentially allow you to impedance match the vibration signal coming from the audio incident on the sensor, and it can modulate the backscatter that comes from the antenna. So the signal that's received back by the, you have a transmit-receive pair of antennas that can be the same antenna. You transmit the radio frequency signal, the sound modulates the reflection back, you get a signal at the received antenna, and you can turn that into the sound output. So now you have something that doesn't require a battery, and it can collect audio and transmit it somewhere. Now you can start to do something interesting with that. So, can I do something interesting? Let's move forward in the video.
What if objects How can Saturn work in the real world? First, let's think about the modern home.
Alexa, play.
Quick question, did anyone notice what book that was? What book was that? Ubicomp 2001 Proceedings. Nevada didn't think I would recognize that, but I said, yeah, I know. So.
Right now, controlling smart home assistants can be tough. You must be in close proximity for the assistant to hear you.
Alexa, stop the music.
Saturn can solve this problem, as it can be easily embedded into everyday objects, like this nightstand.
Alexa, stop the music.
Allowing them to be ubiquitous microphones for interactions and control, extending Alexa's capability to hear from anywhere in the house. Let's look at another example in the home. Saturn can be used for providing in-room context. If we have multiple Saturn patches located on a table, it can help detect the location of people around it by the strength of the signal received.
Hi, how are you?
I'm good, thank you. How about you?
I'm good too. Hi.
So you can basically do relative volume detection to determine who the speaker is. That's what that particular application shows. Okay, so what I'm suggesting here in the 5th generation is that if we can produce examples of these computational materials, and I just showed you one example. I'm not showing you the second example, but if you'd like, it's actually a little more playful and has a variety of different application capabilities. I'm happy to show you after the talk when they turn the cameras off. But if we look at this in terms of this generation, what I'm suggesting are these self-sustainable computational materials. The difference between previous generations is that now the potential is for every person to interact with every object, because every object can be imbued with this computational capability if we think about this to its logical extent. And I've given you some silly initial examples, and what really will push this field forward is coming up with some really compelling uses of it. And I'll try to give you some more serious and compelling examples next. But what do I think will go with this 5th generation? 5 challenges. So now I want to outline 5 computer science and beyond challenges that this 5th generation of computational materials presents. And the first of them is prototyping. How do we produce experiences that matter? And this is motivated by Weiser's point with respect to ubiquitous computing, that the whole reason you're going to be inventing these new technologies is because of the human experience that you might improve with the use of these technologies. So that's what's driving some of this work. So, first example, there are 2 extremes I want you to think about. So that Saturn patch is like a piece of paper, right? Here is a piece of paper, a Post-it note. So can you think of a situation where I might take a Post-it note like this, write a message like, I've left for 5 minutes, leave a message if you want, and then I place it on my door, and when someone shows up, they said, hey, Gregory, you weren't here. I had $1,000 for you, but I guess you don't want it. Okay? And that's a way for me to deploy a way to record and transmit this information. But this is a Post-it note, right? So this is disposable. If we can make it cheaply enough, we can essentially think about these kinds of applications where it is. Weiser talked about the inch scale being disposable, but the inch scale that we ended up getting was this, right? This is not something that you would consider disposable. Something that is inch scale that's disposable is more like a USB flash drive. Right? So we get lots of those, and they're mostly disposable. Okay? But we can think along this line, if it's cheap enough and has interesting capabilities, And I'll talk about there's more than just sound you can do here. That's a disposable application. But the other extreme is to think about enduring applications. So, you know what this is? This Tyvek material? That's a wrap they put around a new construction as a kind of sealing to keep moisture out and other things before they put the external shell on there. Well, Tyvek can be produced at around 8 square meters per second, relatively cheaply, so you can produce it in bulk to wrap around a house. So what if we were able to create the sensing capability that I demonstrated with the Saturn patch, and it could sense phenomena like moisture or imbalance of vibration on a structure. And it could be put in place around the shell of a building and then covered and last for 20, 30, 50 years, but give information, sensing information about that particular building. So those are two extremes that we might think about in terms of how we might deploy or why we might want these kinds of self-sustaining computational materials. I'm going to give some other examples from other work. So this was presented at UbiComp last year by some University of Washington researchers, a battery-free cell phone that leveraged capacitive touch and analog backscatter to allow you to be able to have a device that operates much like a cell phone to facilitate audio conversations, but didn't require its own battery source. Okay? Well, it turns out there's some really interesting work going on here. This work that I saw just this morning, an example of how you might do eye gaze tracking with a device that doesn't require a battery. So some thin solar panels on the stems of a glass that essentially drive paired photodetectors and emitters around the rim of a glass to basically be able to determine the movement of the eye. There's other work that this lab has done here, being able to detect gestures above a watch without needing power to essentially detect that gesture. So there are a lot of people that are inspired by this idea of battery-free, by which we mean using harvested solutions or understanding the motion that's involved in what you're trying to sense to allow you to get information without having to introduce an additional power source. I was here today is Ray here? Dr. Ray Wang, is he here? Please stand up and get your congratulations. So, despite all my efforts to fail him, I failed in my attempt to fail him today. But one of the things that he talked about in his talk was the challenge that exists with being able to collect lots of information from individuals to allow you to be able to understand individual and collective behavior, is that we're trying to leverage people wearing this sensor platform or other wearable sensor platforms, and some of our routines with these platforms don't allow us to wear them all the time. And they're fairly expensive, so it's hard to do a study if you have to give everyone a $250 Garmin device. There's only so many of those you can get. But if you think about that Saturn patch as a strip, or the piece of technology that I have not been able to show you yet, but if you're interested, I will show you after the talk. I think that we're not very far away from being able to create wearable devices that are battery-free that collect some of the physiological data that these other devices, movement and other kinds of physiological objects, and you can create it in a way where it's waterproof, it's relatively durable, doesn't require a battery, so people can wear it 24/7, and you can collect and transmit information. So there are lots of opportunities for some compelling applications. So let's go on to the second challenge, power. Well, I'm not going to give you a lecture on harvesting power. My guess is there are plenty of people in here that know more about harvesting power than I do. But this triboelectric nanogenerator that I talked about is a particular example of using kinetic or movement phenomena to drive or generate an electric current. And it was invented by my colleague Z.L. Wang, a very famous material scientist at Georgia Tech. Probably 2015, I think, was one of the first papers on the triboelectric nanogenerator. Here are some examples of different modes. These different layers here are different kinds of material. In this example, the white is silicon rubber, the gray is a nylon conductive thread, and the brown here is copper wire that has a PVA coating over it. And in this particular construction, there are two things, and imagine that's like a cord form factor. There are two things you can do to induce a triboelectric effect. One is human skin can come in contact with the outer silicone rubber layer, and then move away. So that contact and separation will create a current, and stretching it along its longitudinal axis will cause the inner layers to experience the triboelectric effect, and the coils of wires here act as electrodes that essentially equalize the electric field, producing an electric field. So these are just some examples. And the really interesting thing about the triboelectric effect, as I said, is that it happens between any two materials. But if you pick materials wisely, you can get amplified effects that you're wanting to look for. So there are some interesting ways, and this is something that's been known in the materials world for several years. You look up TENG, and there are thousands of citations to it. But it's relatively unknown in the computer science domain. Hopefully it will become a little more known, because there's lots of ways to exploit this to produce cheap kinds of sensors that are battery-free. Next example is thinking about production. So we have to figure out how to produce how to have manufacturing techniques that give you large-scale computational products from techniques that extend beyond the kind of additive manufacturing techniques that we're already familiar with. I talk about printed electronics. You're probably all familiar with 3D printing and some of the multi-material 3D printing things that we have today, and examples of being able to produce somewhat fully computational devices as printed 3D objects. But before we talk about wanting to extend those techniques, I want to dispel another myth. And that's the myth that computing devices, the transistor, are really cheap to produce at scale. If you think about Moore's Law, and relative to what we could produce in 1940, yes, these devices are really cheap to produce at scale in 2018 compared to 1965, okay, within that particular domain. But we need to look at other things that are manufactured in our everyday life to really understand the gap that computing has compared to other things. So if you plot the cost in dollars to produce a mole of something. So who knows what a mole is? We got any chemists here? How many items are in a mole?
How many atoms?
Yeah. 6.023 times 10 to the 23rd. Excellent. So how much does it cost to produce 10 to the 23rd integrated circuits, silicon field effect transistors, plotted from 1970 to 2020? You see that it costs 10 to the 17th dollars. So Mark Zuckerberg can't even do it. Right? That's a lot. It costs a lot to produce a mole of transistors. But let's look at some other things. Lipitor, chemical molecule, costs about, what, that's $10,000 to produce a mole of Lipitor. Aspirin costs about, what, $50, is that? Gasoline, pennies, to produce a mole of gasoline. So there are lots of things that we manufacture today that are way cheaper than integrated circuits. Now there's an obvious hole in this argument that I'm sure all of you are thinking, but you're afraid to say it because you don't want to embarrass me. So I'll say it for you. Why would I ever want 10 to the 23rd transistors or devices? Well, I'm going to say that you would want it if you had it. But you don't have 10 to the $17. If it was a lot cheaper, then we could put them everywhere. So dispelling this myth that it's cheap to produce transistors. It's cheap relative to transistors 40 years ago. It's not cheap relative to other things that we manufacture. Oh, this little point down here. These other things are manufactured in very different ways. They don't use integrated manufacturing processes. So if we want to move this down, we might think about different ways to manufacture computational devices. Let's think about how much or how fast we can produce these kinds of objects. So if we look at integrated circuits, about maybe 2 years ago, we produced in the world around 3 square miles of integrated circuits the entire year. Okay? Flat panel displays, about 65 square miles per year. Solar cells, about 150 square miles per year. Flat glass, so construction material, 2.4 times 10 to the third, a lot more per year. Drywall, plasterboard, 5 times 10 to the third miles per year. Paper, 5 times 10 to the fifth square miles per year. So there are lots of things that we produce in this world that we produce at a much faster rate, as well as much cheaper than integrated circuits. So arguably, there is a lot of progress that could be made. Right? Maybe we're looking at being able, if we want to produce the Tyvek computational material, we need to be producing it at about the same rate that we produce other kinds of building materials. So that's a target region to go. And there's quite a gap. So there's a lot of progress that needs to be made. Here's why integrated manufacturing processes might not be the way to go. Because this plot shows if you look at the yield rate for every step of an integrated manufacturing process, that means how perfect does it have to be. If you have just 1% defect rate, and you have 100 steps, and 100 steps is not a lot of steps when you're talking about building an integrated circuit, you see the yield quickly drops down to less than 50%. So unless you're going to be super, super, super perfect, then you're going to have a problem with your yield rate if you do an integrated approach. So all these things suggest to us that we might not want to think only about integrated manufacturing techniques, which was what the basis for Moore's Law was all about. We might want to consider other manufacturing processes that are very familiar in the chemical engineering front to try to help us get up to massive scale and much cheaper production of these computational devices. Now let's think about another challenge, platforms. So here I'm talking about talking to the computer architects in the audience. So the Saturn patch connected with analog backscatter is doing much of its work in the analog domain. The reason you're doing that is to save on power. It's interesting, and I am not a computer architect, but I stayed at Holiday Inn Express. I did not last night. I have interacted with a number of these folks, particularly the folks at the University of Washington, and Josh Smith has a very eloquent way of expressing this. A number of different examples where you take a particular system that's trying to solve a particular problem, and what you decide to implement in digital solutions versus analog solutions depends on the problem. It's not always the case you want communication to be done in the analog domain. Sometimes you want it done in the digital domain. It's not always the case that you want computation done in the digital domain. Sometimes you want it done in the analog domain. So on a case-by-case basis, you need a principled way to determine what should be digital and what should be analog in your solution, because you're trying to produce self-sustainable computational capabilities. Oh, this last point here, the architecture. Neuromorphic is interesting because it's modeled after a low-energy analog solution for pattern matching that's done in the human brain. So one way of being able to do local computation on the Saturn acoustic patch is to attach to it something like a fixed field programmable analog array, an analog computing device to do pattern matching on that. So there is hope for being able to produce local computation that can be powered by the extra power budget that's available from the Triboelectric nanogenerator. Last thing, I talked about being able to have computational material be everywhere. And I showed that chart that said that every person will be in touch with every object. Because in some sense, unless I could magically suspend myself in the air, I come in contact with some material. And that material comes in contact with other materials, and so on and so on and so on. So you're basically, everyone is connected to everything, ultimately. Which is either really exciting or unbelievably scary. Right? So you need to think about values that you use to drive what you're going to use these technologies for. And one of the prime values is one of privacy. And I've been working with a number of colleagues that come from the kind of technology and policy side of privacy, and their attitude about this is, well, there are actually some interesting challenges and opportunities in a world that has computational materials where you might be able to implement privacy capabilities that you cannot do in a non-computationally empowered world. So there are challenges, but there are also opportunities. And there are other values that you might think about in terms of sustainability, what materials you use. If I'm thinking about producing disposable computational material, I'd better worry about how this degrades over time. Now there's one more P I want to leave you with before I end, and that is the most important P of all, and that's people. So up here, I show the images of a number of my colleagues over the last 2.5 years that I've been working with to try to build this vision of computational material. And we go under the name of Cosmos. It started with Computational Services for Multi-Object Systems, Cosmos. Don't worry about it. This is like IBM. Don't worry about what the words stand for. Think about Cosmos, right? We're shooting for the stars. It's Cosmos. And when I was bold, and I was younger, and I was more ignorant about 2 years ago, I had something that I referred to that was my competitor to Moore's Law, which I call the Cosmos conjecture, which is essentially what kind of rate of manufacturing progress do we have to have for computational materials that would mimic Moore's Law, but would be about the speed and cost and the production rate of computational materials. And if you have the same kind of every 18-month doubling factor, and we go from now to about 20 years, we go from the ability now to produce about 3 square miles of computational integrated circuits to things that are building level within 20 years. Right? So, but I don't have empirical evidence. That's why it's the Cosmos conjecture. Also, why it's not called Abowd's law is because if it's wrong, they're going to blame Cosmos. Right? So it's a conjecture because I don't have empirical evidence. It's not named after me so that I don't become infamous. But the interesting thing I want to point out about this set of people is the number of disciplines that they represent. There are material scientists, so I want to particularly thank Eric Vogel and Mike Filler. These are the material scientists and chemical engineer that first approached me about this idea. And they provided some of those slides I showed that demonstrated the production rates and the cost of producing materials. We've got electrical engineers, we have computer architects, we have people like myself that are interested in human-computer interaction and design and applications of this. And the reason I show this particular slide is, what does this mean for students who are interested in this? Okay, when computing started, Generation 1, if you were going to be a researcher in that field, you needed to be able to build the device, the vacuum tubes, and connect them all together, and program the device, which was typically physically manipulating wires and switches. As the field matured, as computers matured, we started to separate into people that did hardware only and people that did software only. And we were very happy from like the late 60s until the late 80s. And then Weiser introduces this vision of ubiquitous computing. And if you want to make progress in ubiquitous computing, you're going to have to bring in some software plus electronic skill, because we're going to add some sensing into this world. So we had a generation of students who realized that they couldn't just be hardware only or software only. They needed to bring those skills back together. We're still there. In this 5th generation, now you have to understand about the materials and maybe the manufacturing process in order to really have an impact. So don't be afraid of this. Grasp the opportunity and learn about these fields, and you will remain relevant for 20 years. The rest of us dinosaurs are not going to be relevant. Here are some of the students that have worked with me over the last 2 years that have taken on this challenge of learning about materials, manufacturing, electrical engineering, design, as well as computer architecture. And they have produced the evidence, the demonstration I showed you. And, oh, did I mention? Of another one that some of them had produced. So I want to just stop by giving you some parting words here. And that's about this notion of self-sustaining computational materials. It can release us from what I consider the shackles, the constraints of Moore's Law, exclusive Moore's Law thinking, where you think really in terms of smaller and faster will always come. And it might drive the next 20 or 30 years of creativity with computing, where we'll think in terms of cheaper and larger scale will always come. And what does that mean in terms of how we might be creative and what we might prototype? So computational materials by themselves, the standalone, that Saturn patch, if I brought in here and demonstrated to you, you say, oh, that's sweet. That's nice. It's a microphone. Woo. Well, it's also a vibration detector. So woo-hoo, right? I could put it on the floor and when I step on it, you'd be able to know, so woo-hoo. I admit that by themselves, they're not that compelling. What's compelling is if you can create them cheaply enough and spread them more ubiquitously around your environment, then the compelling applications can emerge. So the mass provisioning of computational material can be very powerful, and that's what I'm trying to inspire us to try to look to. And I believe that it's not going to be the Intels of the world that are going to be the leaders in this, because they're pretty much committed to the integrated manufacturing process, and it's quite a significant shift in their mindset. It's the other kinds of manufacturers of the world, the Dow Chemicals, the Corning, those people that create these kinds of materials, the manufacturers of Tyvek. Those are the ones that might become the leaders of this alternative computing revolution, or some of you may produce your own small companies that 10 years from now you will be Mark Zuckerberg or Gordon Moore, or name your famous computing billionaire. So my whole goal in doing this talk was to inspire you. Now, throughout the day, I've been talking to a number of you about some of these ideas, so what you've heard here, you've had hours to digest already, and you're probably thinking about what you like about this and what you don't like about this. So I thank you for your attention, and I am open to any kind of criticisms or discussions about this idea. Thank you very much. And we're done on time. I promise I do not have any computational microphones here recording what you say.
So, with the use case that you showed in the video of someone giving instructions to their Amazon Echo, how long does information that you collect through this kind of material linger?
So all that's doing is collecting the audio signal and transmitting it to Alexa. So your answer is the same as it is today. How long does Amazon keep the audio when you say, hey Alexa, what's the weather at Dartmouth today? So this computational material is not storing it. It's just collecting it and transmitting it. If you add storage, then your question becomes very relevant. And I am interested. We've demonstrated that the Saturn patch harvests enough energy in addition to the vibrational source and recording that. If you put a thresholding on there, you could flip a bit, right? So we show we have enough energy to do that. So you can just store, for example, it was loud enough here, or I knocked loudly enough. So something was here. That's all we can store now, but I'm sure we're going to be able to come up with low energy or better harvesting techniques to be able to collect information longer, and then your question becomes much more relevant. How long will this carpet keep information that it was stepped upon? And if my shoe has idea of me that Gregory Abowd stepped there, then it becomes a really interesting question.
Would you have other kind of sensor with this implementation, like magnetometer or other sensor?
I'm sorry, say that again?
Would you have other types of sensor with this technology, like magnetometer or?
Oh, yes. So what I showed was what I call a self-sustaining sensor. So it's sensing, the phenomenon it's sensing is what it's harvesting the power from. But you can certainly look at situations. So, for example, the eye gaze tracker that they've developed here in Dartmouth, that's using solar harvesting to drive a series of IR photodiodes, right? So you can certainly think about doing that. The problem is those other sensors have a particular budget of energy that you have to meet, and they usually have an activation energy, that threshold you have to overcome in order to get them to then work. I am fairly confident that within the next year or so, we'll be able to produce something that can harvest enough energy to essentially drive the collection of data from at least a one-axis accelerometer, hopefully a three-axis accelerometer. And the interesting thing about that is that it will take advantage of the fact that when you've got something around your wrist, as it moves around, every time it makes contact and separation from your skin, it's generating triboelectricity, and as you move, the wind causes some triboelectricity, and as you manipulate your hand, you're also generating some energy. And if you have some way of being able to collect that power, you can then drive and store information. We have something under review now that I wasn't talking about, it's not the video I'm talking about, where you're looking at harvesting ambient FM signals to drive wireless communication devices. So there are a variety of ways where you might use a different kind of signal to harvest energy from to drive the sensing from another device. But that's not what I've shown you here. Is that here and then here?
You were talking about a mole of aspirin, a mole of what is the unit there? Is it a molecule?
Yeah, molecule. Mm-hmm.
little unfair. An integrated circuit is good in itself. One molecule of aspirin is not so useful.
That was the second question that I was expecting someone to say. Right? Currently, that's right. A transistor by itself, we don't think is that useful. However, the example of Saturn matched to the antenna used a single transistor to do the impedance matching to allow the backscatter. So, yeah. You're right. It's not fair, but still, 10 to the 17th. Okay, I'll give you a few orders of magnitude.
What is the comparison for aspirin tablets? What's the mole of aspirin tablets cost?
That's a good question. I don't know the answer to that. I'll ask Mike. They're still cheaper. I know we head down here.
Really interesting talk, really interesting topic. I'm just
But-
curious about the long-term implications of this kind of vision. Say we can produce these billions and billions and billions of these kinds of sensors. We could potentially be producing a lot of waste. Is it possible is there any work being done to investigate possibly biodegradable applications of this?
Yeah, so when I was talking about the privacy one, I just mentioned in passing other values that you might apply to this, and that's the materials you use. If you're thinking about disposable, if you're thinking about the durable case, then it's less of an issue. But I'm thinking something that's going to last a few days, you do need to worry about what materials it's made of. And we have to think about that. So the current Saturn one is using copper, PTFE, and paper. So at least two of those are not wonderful. But at least one of those, copper, is something you can harvest back and reuse. So, yes?
Do you envision any planned obsolescence or a way to deal with compromised device from security or privacy?
Okay, those are I view those as two very different, very significant. So planned obsolescence and so remind me of the security privacy after I.
Sure, like a possible software update.
Yes. So the computer architects that we work with see things like the Saturn patch with the single JFET in the antenna, and they go, oh, that's great. It can do one thing. I want a material that I can program to do other things. And I think there are two responses to that. I said, yes, you're right. Okay? So I need to be able to produce at least 100 or so assembled cheap devices so that it can be programmable to do something. But I can also say that single-purpose materials don't necessarily have to be very multifunctional. Right? So it's something that can detect the vibrations here, maybe writing on top of here. There's a lot I can do without making this suddenly be able to sense temperature by flashing it with a new a program inside it. So until we can assemble thousands and tens of thousands of these devices in the computational material, I don't think we're going to really interest the computer architects in this world. So you're right. These things are not very programmable yet. Now, your question about security and privacy, what is that? Because that's different to me from something being flexible.
In the event that, say it was very easy for someone, a third party, to collect mic-based information of acoustic signals, and if these devices persist for tens of years, that seems like a big risk.
Yeah, absolutely. So the inspiration for being able to use do the analog backscatter to get the audio signal off the particular sensor was actually a trick that the Russians played on the U.S. It was either in the 40s or 50s. They gave this gift of the American seal to the American embassy in Russia, in Moscow, and they placed it in their office. And then the Russians beamed a very high-intensity radio signal from way far away, bounced it off that seal, and they essentially had a bug. Right? That's the inspiration. So yes, you can see nefarious uses for this. This particular technology, for better or for worse, is pretty near field. So you have to be relatively close to it in order for it to get your sound, so like about this distance. And how far that receive-transmit path goes is a function of how strong that signal is. Ultimately, I want to be able to work with something like your mobile phone, and you're not going to want to put out a lot of energy there. So you're going to have to be relatively close to the infrastructure in order to be able to bug it. So someone's going to have to, maybe the cleaning staff. So this is the way you're going to make the Saturn patch be really big. Someone with the cleaning staff goes around with the big vacuum, and essentially it's got the radio signal that's going to be collecting things, but it's only collecting things in real time. There's no storage here. So there is this potential of being able to sweep to pull information, but you have some limit in terms of how powerful a radio signal you're allowed to essentially shoot toward this. And I'm looking to do it with the kind of infrastructure, Wi-Fi or phone levels of RF signal. So, but it is something to think about. Yeah.
I had a question about your omnidirectionality of your microphone. So the orientation.
It's not.
Yeah. So I imagine the orientation is very. You have to be speaking kind of like right at it. Like if you're at a.
Not right at it. In the paper, it shows where you have to be relative to it. We also studied how curved it could be, so we can see how you might deploy it. Yes, you will change the characteristics of this as a microphone based on its geometry. That can be an advantage or a disadvantage. But the fact is, you can put these in lots of places, and you can bend them to be in corners and things. You could put them on fabric. So it has a flexible form factor that introduces things that you can't get with commodity passive electret microphones today.
Okay, folks, it's not your fault, Gregory. Gregory is pioneer in our field, and it's basically spearheading the next new thing. So I'm going to ask you, Gregory, this is our last question. Will this help phones disappear eventually?
So some of my colleagues want desperately to produce output, want me to focus on doing output. And I think there's a hope with electrochromic materials, very low power activated display technologies where you might be able to put displays in your environment so that you wouldn't have to carry this around. And you could have a phone capability follow you, but I can't give you a guess.
Can you give us a date?
A date? Do you remember the Cosmos conjecture? I'll give you a Cosmos date for that. So yeah, I think easily within 40 years.
Okay. On that note, I'd like to thank both of you.